This presentation is about ultra-fast inclusion analysis with the ARL iSpark, a Spark OES spectrometer. Today I will start the presentation with the inclusions and the importance to control them. And then I will continue with the principle of this inclusion analysis with the ARL iSpark, followed by some examples of application of inclusion analysis with the ARL iSpark. And finally, I will present you the latest software tool for inclusion analysis. So the first section of this presentation is about inclusion and the importance to control them. What are the inclusions? Inclusions are small particles embedded in the steel matrix. They can be formed in the liquid steel by chemical reaction, and they are called endogenous inclusion, or they can be due to contact with refractories and slag. In this case, they are called exogenous inclusions. Most frequently, they are called non-metallic inclusion or NMIs. These inclusions have different compositions. They can be oxides of different types, sulfides, silicates, nitrites, and even others. These inclusions have a wide range of sizes, from microscopic to macroscopic, and also large variety of morphologies and structures. You have some example on the right side pictures. So these pictures are not, of course, optical emission pictures, but scanning electron microscope picture of inclusion extracted by leaching process. The importance of the inclusion is due to several things. First, the inclusions are always present in steel. Their extent depends on the steel grade and on the production process. Second, the inclusion strongly affect the steel quality and the production process. Inclusion affect the steel quality. So steel properties strongly depend on the inclusion content. Some examples are the resistance to fatigue, the weldability, formability, or the machinability. Some of the inclusions are needed to impart certain properties. For example, manganese sulfide for machinability of free cutting steel. However, many are unwanted because they have negative impact on the steel quality and the process stability. Inclusion affects the steel quality. What are the consequences of a bad inclusion contents? There can be different possibilities, from non-conform mechanical properties to failures of the finished product, or to steel defects appearing at the rolling mill. This is what we see on the picture. What happens when a hard inclusion goes through rolling mill? As you can see on the lower right picture, there is creation of some defect of the matrix due to the fact that the inclusion is not broken. And this kind of defect is happening in the direction of the rolling direction. So these kind of things frequently results in very costly bad hits. In other words, hits that are scrapped or degraded or customer claims. I said that inclusion also affects the process. This is a famous example. Actually, a very common issue for the steel makers. Clogging of the submerged entry nozzle is taking place when aluminum is added for the oxidation of the steel. This causes the formation of aluminum oxide inclusion that crystallize and clog the nozzle. So Steel makers, you can see a few pictures. No? That's very interesting. Here you see the effect of inclusion crystallized in this nozzle. So the steel makers have to change that. Process is interrupted, and in many cases, some steel has to be scrapped. So this is all very costly. So how to reduce the cost of the inclusion analysis? So trust steel makers. They try everything and use all the possible analytical methods to control the inclusion and avoid quality and process problem. The modern and probably most known techniques nowadays is SEMIDX. This is really the reference technique, combining scanning electron microscopy and energy dispersive X-ray fluorescence. This technique has the advantage of being quantitative and compliant with inclusion analysis norms. However, it has a main drawback. The analysis cycle is long. With SEMIDX, it takes, in best case, about 1 hour, but in many cases up to several hours for sample polishing and analysis. So this is too long if the steelmaker wants to rapidly control the inclusions. A faster alternative is given by the optical emission spectrometer. The ARL iSpark, our latest generation of instrument, combines high performance elemental analysis and the most advanced inclusion analysis of its category. Concentrations and inclusion data can be obtained from the same measurement. The benefits of using the ARL iSpark are several. In the analytical workflow, it is an ultra-fast analysis that takes about 1 minute for an average of 2 measurements, exactly what the steel makers used to doing with an optical emission spectrometer. It is a 2-in-1 analysis. It means that composition and inclusion are obtained at the same time. Sample preparation is fast because the standard OES preparation is used, which means that no polishing is needed. Overall, the analysis workflow is short. It takes 5 to 10 minutes from sampling liquid steel to obtaining the results. And a high throughput of sample analysis is possible because optical emission is very quick. Hundreds of samples can be analyzed typically per day. There are actually more benefits of using the ARL iSpark for inclusion analysis. One is low investment cost because the standard OES instrument is used. There is no extra maintenance. The standard one applies. The instrument is easy to operate, which means operator does not need to have special skills for this inclusion analysis. And then the method we deliver are turnkey. They are factory customized and ready for use at delivery of the instrument. Finally, the inclusion analysis with the ARL iSpark is suitable for automation, which means that we can automate the instrument with an ARL sample manipulation system. You have a picture on the right side of an ARL iSpark automated with SMS 2300. So in conclusion, with the ARL iSpark, there are more reasons to perform inclusion analysis than not. In a 3-year-long project on inclusion analysis, several European steel companies, you have some name on the bottom of the slide, Several European steel companies have evaluated the benefits of inclusion analysis with optical emission spectrometer. They concluded the following. First, saving for one avoided customer claim corresponds to $100 kilo in average. Second, saving for one avoided bad heat corresponds to about $130 kilo in average. And third, in a year, a steel plant has to face typically 5 claims and several bad heats. This means that avoiding claims and heats problems allows savings of more than $500,000 per year, which is clearly much more than the price of the optical emission spectrometer. The European steelmakers also concluded that the best opportunities for savings on inclusion cost were at secondary metallurgy, where inclusion analysis allows to take corrective action on the inclusion contents. So steel treatments can be adapted in order to correct for bad inclusion contents. Another place is at continuous casting, where optical emission gives early warning for problems like clogging, the problem we've seen just before. And on the final product, where optical emission is a low-cost inclusion control method. So these are the 3 places where steelmakers recommended to use optical emission inclusion analysis. There are, of course, other possibilities to use this technique. Now we have discussed inclusion and cost. Let's go to the principle of the inclusion analysis with the ARL iSpark. I say with the ARL iSpark because there are several ways to do that. I think our method is unique, and I prefer presenting the specificity of our technology and methods. So the basic principle of signal acquisition for inclusion analysis is the same as the one used for elemental analysis. That's why the 2 analyses can be combined in the same measurement. Thousands of single sparks are repeated at high pace between the electrode and the sample. At each single spark, a small part of the sample is ablated and atomized, and a light pulse is emitted. This light pulse is characteristic of the atoms present in the sample and of their quantity. The light pulses are then dispersed into spectrometer optics in the emission wavelengths of the elements contained in the sample, and they are then transformed into electrical signal, which are characteristics of the element in the photo multiplying detectors. At the end of this acquisition, single spark signals, so-called single spark signals, are obtained. Signal processing is where elemental analysis and inclusion analysis differ. For the standard OES elemental analysis, the single spark signals are integrated before being transformed into concentration by using calibration curves. For the inclusion analysis, the single spark signals undergo statistical treatment and calculation in order to obtain inclusion data and properties. To understand the principles of the inclusion analysis, the single spark signal are represented in run charts. with intensity on the vertical axis and number of the single spark on the horizontal axis. Here is an example of an aluminum run chart. On this chart, the peaks are the signals due to the inclusion. You see here different peaks obtained with different single sparks. The peaks are the signals due to the inclusion that contain at least some aluminum. The intensity of the signal of the peak is proportional to the size of the inclusion. In the practice, peaks are identified as signals with an intensity higher than a threshold. In many cases, we use 3 sigma to discriminate peaks from noise, but the threshold can also be set higher when only a larger inclusion needs to be detected. On this other slide, the run chart of the element calcium has been added. When a coincidence of an aluminum peak with a calcium peak, like here, is observed, it signifies that the inclusion contains both aluminum and calcium. The inclusion is therefore likely a calcium aluminate. When no coincidence peak exists on the calcium channel, it signifies that the inclusion contains aluminum but no calcium. In this case, the inclusion is likely an aluminum oxide. So this is the basic principles of the inclusion analysis, where we count number of peaks and number of coincident peaks in order to evaluate the number of inclusion and their compositions. And second, we measure the peak intensities to evaluate the size of the inclusion. The raw data presented here in the form of run charts on the various element channels. The raw data is transformed into inclusion data or properties by using statistical algorithms, so-called Spark-Dat algorithm, some mathematics, and some chemistry. 2 types of data can be obtained: the simple inclusion data or properties, and the advanced inclusion data and properties. We'll see the difference in the following slides. At this point, I think it's useful to tell a few things about practical aspects of the inclusion analysis with the Spark OES. The first thing to mention is sample preparation. So there are several ways to prepare a sample for optical emission. As you know, milling is recommended in many cases. And it is the case also for the inclusion analysis when advanced inclusion data and properties want to be evaluated. It is also, of course, the best choice for the simple data and properties. The reason is that by milling the sample, all contamination of the surface is avoided. You know, contaminating surface with grinding aluminum oxide paper could lead to the situation where you count an increased number of aluminum oxide inclusion during the analysis. So grinding is normally avoided, but it's still possible and suitable for the simple inclusion data and properties, which are less quantitative than the advanced ones. Some details of the analysis. In this table, I put the duration for one measurement analysis, 2 measurement analysis, and 6 measurement analysis. You can see for one, how we call run, 22 seconds allow you to get the concentrations and the inclusion results. For 2 measurements, about 1 minute is needed. 2 measurement is typically the type of analysis that steel makers used to doing on the steel samples in the production control. So in this case, 1 minute is still the time necessary, like for normal optical emission analysis. Interesting is to look at what surface of the sample is evaluated with our technique. So for 2 measurements, it's about 40 square millimeter of the surface where we look for inclusions. As you know, in optical emission, material is ablated. So the analysis is not a 2-dimensional method, but a 3-dimensional one. So we can talk about volume evaluated as well. And in the case of a 2-measurement analysis, the volume is 0.08 cubic millimeter typically. This corresponds to a mass that is evaluated of the steel sample of about 0.66 milligrams. Finally, I want to mention that the domain of application is limited to micro-inclusion with size of about 0.5 to 15 micrometer, excuse me, the typo, micrometer, depending on the type of inclusion and the sample. So there is no way to look at macro inclusion with the SPARC OES. Let's now move to some examples of application of the inclusion analysis with the ARL iSpark. First, the simple inclusion data and properties. This is a qualitative evaluation of the number and size by inclusion type. The properties and data of the inclusion are obtained in the form of peak counts and counts of peak coincidences, exactly what I showed you before. Intensity is also used in this kind of evaluation to classify the inclusion as SML or small, medium, and large. The normal way to work with this kind of data is to use reference samples. In other words, compare results with those obtained on known samples, typically good ones and bad ones, in terms of the inclusion content. You have here an example of determination of number of peaks for low alloy steel samples. You see different elements that have been evaluated in terms of small inclusion number, medium size inclusion number, and large size inclusion number for total number on the right side. These numbers are per cubic millimeter. Peak coincidences are also evaluated. These are the different coincidences. I think Kaizen will explain you a little bit the nomenclature in the live demo after this presentation. And also here you can discriminate small, medium, and large inclusion and count them, or you can just consider the total of the small, medium, and large. So this SML, small, medium, large classification is very interesting. Inclusion criticality depends on the size. So not only the number of inclusion is important, but also their size. So normally large inclusions are more critical than medium ones, which are more critical than the small ones. So here you see how we do that. The relative sizes SML are obtained by using different detection threshold, as you can see on this calcium run chart. One threshold to detect the small one to detect the medium, and one to detect the large inclusions. You can do that on all the elements, and at the end, you obtain the counts for the different categories of inclusion. So this is very interesting, knowing that criticality is not the same in all the steel grades or for all the customers. So with this kind of method, you can adjust the control parameter to the need. For example, for the less demanding steel grades or customer specification, you will count only the large inclusion. And for very demanding grades or customer specification, you will count all the inclusion, small, medium, and large. In this example, we have counted peaks and peak coincidence in samples from two different heats, of course, of the same steel grade. So maybe not necessary to mention that if you measure them with optical emission, you would measure the same composition. So as you can see in the run charts, the sample of heat 1 and heat 2 have pretty different inclusion content. So by using very simple algorithm to count the peaks, aluminum total number of peak, oxygen, calcium, sulfur peaks, and some coincident peak corresponding to aluminum oxide, calcium aluminate, calcium oxide, and sulfide, we very quickly realized that the inclusion content is very different in the two samples. The sample of heat 1 contains only calcium inclusion, oxides and sulfides mostly, while the sample of heat 2 contains mainly calcium aluminates and aluminum oxides. So very, very different content of the two samples, which have probably some consequences in some applications or for some customers. An application for that is, of course, steel quality, but it can be used also to control the inclusions and reduce nozzle clogging and problems at casting. So let me now just come back to nozzle clogging. We've mentioned that inclusion analysis with optical emission allows to reduce nozzle clogging. So just back to how it is caused. When aluminum is added for deoxidizing the steel, there is generation of aluminum oxide inclusion. This inclusion will crystallize and clog the nozzle. Now you have an example of an aluminum oxide inclusion. So steel makers normally perform some steel treatment. They add calcium compounds to modify the aluminum inclusion into calcium aluminate inclusion that are liquid in the liquid steel and will move to the slag. When you do that, the consequence is that you reduce of course, the risk of clogging and extend the nozzle lifetime. You have here an example of an inclusion that is modified from aluminum oxide to calcium aluminate. Now, when steel makers put calcium additive in excess, there might be the formation of calcium sulfide inclusion that are also problematic because they cause problem at the casting. So the solution to control that and get only calcium aluminate inclusion and no aluminum oxide or no calcium sulfide inclusion is to control the addition of the calcium compounds by monitoring the peaks and coincidence corresponding to aluminum oxide, calcium aluminate, and calcium sulfide. So the idea is that when aluminum oxide inclusion increase and calcium aluminate inclusion decrease, you have to add more calcium compounds, and when calcium sulfide increases and calcium aluminate decreases, less calcium compounds have to be added in order to have a smooth process. All this can be done optimally when using statistical process control software. SPC software. We'll see the application at the end of this presentation, where you can control the level of these different inclusion in a very simple way. Now let's see a few examples of the advanced inclusion data and properties that can also be obtained with optical emission. This is a more quantitative evaluation of many different properties by inclusion type. So some examples are number of inclusion. I don't say number of peaks in this case, but number of inclusion, size and size distribution in micrometer of the inclusion. This size is what we call the equivalent spherical diameter, or ESD, because the optical emission is a three-dimensional techniques that allows to see not only the inclusion from the surface, but also in the volume. What we can also typically evaluate is the volume fraction for different type of inclusion, their concentration, and also special application is a determination of the total oxygen content. This is an example of inclusion size distribution obtained with this kind of methods. You have here different type of inclusion: alumina, calcium aluminate, spinel, calcium sulfide, manganese sulfide, and you have for different size classes and for all the size classes together the number of inclusions that are monitored. Another example is the inclusion volume fraction. Again, for the same inclusion, now you have an evaluation of the fraction of the volume for the inclusion in the different classes and for the total. An interesting application was obtained with a customer. We measured two of his low alloy steel samples. Actually, we measured the aluminum oxides to check their distribution. The two samples were produced with different scrap qualities. The first one in blue, where is a sample taken from a heat produced with sorted scrap. So in principle, scrap with less with more purity, and the red one are a sample from a heat produced with unsorted scrap, so scrap of different sources. So the red one is in principle cheaper than the blue one. As you can see on the graph, there are more inclusion which are monitored with the heats produced with uncertain scrap, and there are also more of the biggest inclusion. So clearly, cleaner steel is obtained with better scrap. So considering this, you can make very interesting things. When purchasing scrap, you can really dedicate the best scrap for the best steel quality or grades and use the lowest quality of scrap for less demanding application and customers. So this is also a way to adjust your cost. I mentioned total oxygen content. With key steel, optical emission inclusion analysis offers very interesting possibility to determine extremely low level of oxygen, which are typically not possible with the standard calibration method. Examples of type of steel where oxygen has to be measured at very low concentration is given in this table. So typically cases where oxygen is around 10 to 40 ppm of oxygen. So normally the detection limit of the instrument does not allow measuring that with good precision and accuracy. The solution is given by the inclusion analysis, and we calculate the oxygen concentration from the content of oxide. Here you have an example of samples, killed steel samples from continuous casting mode that were measured with a combustion analyzer and with the Spark OES. You can see all the concentration, all the samples are below 30 ppm oxygen, so normally not possible to analyze by optical emission. But with the inclusion analysis, we are able to obtain a good match of the concentration obtained with the combustion analysis down to very low amount of oxygen. On the right side, we have measured certified low alloy steel samples. So we compare the Spark OES result in blue with the certified value of the samples. And here again, you can see that for all the measured samples and down to a few ppm, there is an excellent match with the reference. So very interesting. The standard method for this kind of analysis is normally combustion analysis, and we see here that optical emission offers an interesting alternative, or is a good candidate to replace this costly kind of analysis. Nothing is possible without software, at least for the analysis. So before finishing, let me briefly present our software tools dedicated to inclusion analysis. Note that some of these tools will also be part of the demonstration by Kaizen in a few minutes. So the software tools, there are different things. At the heart of the inclusion analysis, there is the analytical software OXAS. So what we call the Spark, that features which are useful for the inclusion analysis are fully integrated in the analytical software, which allows, for example, parameterization of the inclusion analysis algorithm and methods. Now there are also a few options, software options, which belong to the so-called SparkDat software suite. The first one is the Spark Explorer. There is also the inclusions report, the ternary diagram, and SPC. The next slide, I give a brief overview of these different tools. The Spark Explorer first, it's a set of software modules for offline work. We mentioned a lot the necessity to analyze inclusion online, so during the process for steel makers, but sometime offline is needed. Examples, to scrutinize the raw inclusion data when there is a quality or a process issue. So sometimes the inclusion data and properties monitored online are not sufficient to understand the problem or the cause of the problem, and it's good to have a look at the raw data. Or also scrutinize the raw inclusion data when inclusion analysis results are ambiguous. This may happen. I think it happens as well with SEM EDX technique. Of course, it's very useful if you want to optimize the inclusion analysis parameters, for instance, the detection threshold, or when you want to compare the raw inclusion data of different samples and measurements. So you see there are a few different screens of this tool, different modules. One we call the quick preview. It's a very nice tool where you can have a very quick comparison of the run charts on the different elements, eventually on different samples as well. You can also see the histograms, the size distribution of the inclusion in terms of element. So here, of course, you have a module to look at the histograms, and you have module to look at the run charts. Especially this one is interesting because you can compare many different channels or samples. Kajan will briefly present you this tool afterwards. Another tool is called the Inclusions Report. It's a digest of the inclusion information. You can see here a few pages of this report. I think Kajan will also scroll through the different things that can be reported in that, but you can see there are different type of information, including peak coincidence counts, or some histograms of the distribution, or even the ternary diagram. So this report is ideal when you need to report the results of an inclusion analysis to the concerned people, who can be quality manager, of course, but also R&D and process scientists or defectology specialists. Typically, some people who also would like the results of a SEM EDX analysis. This report can be customized to meet your needs, like it is the case with the inclusion analysis method. I mentioned the ternary diagram, so phase diagrams of inclusion systems with 3 chemical components, for example, aluminum oxide, calcium oxide, and magnesium oxide. So these 3 compounds are on the corners of the triangle. These kind of diagrams are frequently used to check inclusion modification induced by steel treatment. Just what I mentioned before, adding calcium and seeing along the process include aluminum oxides being transformed into calcium aluminates. So these kind of diagrams are very popular, almost the natural language of inclusion specialists. So in these diagrams, you can see different things. Of course, the size classes that can be customized, size classes in micrometer, the average composition in the form of numbers and a point on the ternary diagram, and class frequency, so number of inclusion in the different classes. You can set up different type of ternary diagram based on the inclusion content or of your sample, or just based on their grade. And finally, SPC software, statistical process control, which is actually a third-party software called Synergy 1000. This is used for online control of inclusion in the most easy way. So critical inclusions, like in the right-hand side diagram, a large aluminum inclusion. Critical inclusion properties can be exported to this tool. and for optimal control of the steel quality and the process stability. This kind of SPC tool is perfect for the steel plant that wants to minimize non-compliant products, rework and scrap, or to minimize process issues like the clogging. You have an example, as I mentioned, on the right side, we have monitored the large aluminum oxides, which are the most criticals. Here are the different samples measured, number of aluminum oxides measured, and USL is what we call the upper specification limit above which a number are considered to be too high. So in this example, for sample number 30, it was found that the number of aluminum inclusion is above the upper specification limit, meaning that the content of inclusion is not compliant. A few concluding remarks, and then we can go for a few questions if there are. The ARL iSpark is the first instrument steelmakers needed for inclusion analysis. It allows almost real-time control of the inclusions in the process in up to hundreds of samples per day, and the investment cost is low. The ARL iSpark is ready to use at delivery with the inclusion analysis methods. It is the solution to minimize the cost of the inclusion and guarantee steel quality and a smoothly running process.
Everyone, welcome to my demo lab remotely. So here is our demo lab in the factory in Switzerland equivalent. And you will see this iSpark instrument. That's the one we are going to measure some samples. Okay, you see other iSpark instrument depending on the application difference. So to be able to see clearly how I operate and measure a sample, I will place now the camera very close to the stand. Okay, so you will be able to see when I am operating. I'll just start to measure 2 samples, as we will normally do. Make one inclusion analysis. I select the task, the method, and type the sample name. Okay, start. Well, it's not too nice. So you will see the sample. I use the milling machine. So it's prepared like that. It's a lollipop sample. As normal analysis, I make 2 runs. during the analysis, we have the list of the results for inclusion, but for the moment, there's no results yet because the way we treat the data, you will get it after the analysis when you finish. So you see the results now. And in order to compare something, I make another sample analyze with a different type. You will see. Now it's sample 2. Now let's finish. So what you can see from here, besides the normal concentration results, here are some listed results for inclusion analysis. We have listed here like peak count for aluminum, for calcium, for magnesium, which are most interested element for forming inclusions. And here peak count total is the total number. And we normalized the number to the cubic millimeter. So for that way, you are able to compare between different method conditions. And we have this small, medium, large groups for the peak count. That's depending on the threshold defined according to the intensity level. So it's like a qualitative size separations. And then after that, you have also some listed inclusion type we defined. For example, alumina or calcium aluminate of spinel. This kind of number, we can also count that and normalize to cubic millimeter with the average from the 2 rounds. We are also able to say combine all the defined oxides. Then we see what would be the oxygen in the number and what would be the sulfides in the number. That's for this type of the method. We are able to count the number. In another type of the method, another option of the method, we are able to count the concentration. Well, anyway, here we have the calcium aluminum ratio. So that is one parameter very useful when you want to count to evaluate what would be the situation with the calcium addition related with the melt treatment. So that's the result you can obtain as normally you can obtain for the concentration. And those results, if we they are automatically saved once we click the finish, if you remember. Those results can be exported like in Excel if you want to study it to, for example, I just put into desktop. And okay, from method, Okay, from different format, we can choose the format. Okay, so if you want to treat the results in the third-party program like Excel, which quite common for the people to use, then you can treat the data like that. You can export, or it is possible to print report. Depending on the purpose, you can print the report as different format, only for concentration or for the inclusion result. Now I will show you with the inclusions report. I print only with the preview, so we see from the screen. Okay. So now you will see here are the report. Depending on the different options, of course, the content of the report will be different. But basically, with our inclusions report, the beginning of it will always showing you the sample and analysis details. For example, here you see the details of the analysis and the calculations. How many runs we made, how many sparks we used to make the statistical calculation. As you know, for this inclusion analysis with OES, the fundamental part is a statistic study. So we need to know exactly which data set we used actually. And then you have this like updated the surface, updated volume or mass. So those are very interesting parameters if you would like to compare with other technique for inclusion analysis. Then after that, you will have the field we kept for showing you the sample composition, because with the inclusion analysis with OES, it's important to know the sample quality or sample type. Sometimes with different types, the conclusions can be totally different, even with the same amount of the inclusion content. Then you have the field of main indices. Here you will be able to put whatever the most important results of inclusion to you according to your purpose. For example, here I just showed the aluminum and the calcium peak count, calcium aluminum ratio, and oxides concentration and sulfides concentration. Then you have another field called a factor, where you can, here this factor is one parameter suggested by some European steel makers. According to them, this can be used as the cleanness index for the process control. This factor is defined as the insoluble fraction multiply the number of peaks for one specified element. So that means this parameter is not only considering the peak count for each element, but also considering the size of the inclusions, because the size of inclusion related to the insoluble fraction, the intensity level. So when you have the bigger size, you will have higher intensity level, and that is calculated this part. So that is one parameter. Then you have this commonly understandable parameter for inclusion concentration. It's just those we have by default about 11 inclusion types we predefined. And of course, the type of inclusions can be added or deleted according to your wish. That's what we call customization. And then you have also this the quite simple part, quite simple results. We call it the standard or the simple option of the inclusion analysis, because it counts as just peak events with single elements or with some coincidence or non-coincidence between the elements. For example, here means coincidence between aluminum and oxygen, and here means coincidence between aluminum and oxygen and non-coincident to calcium. So by this way, we count the peak number, and we are able to, if we are experienced, we are able to estimate what type of inclusions we can get. So of course, the purpose for this part, if without the option of advanced inclusion analysis, then from this part, people are already able to get some information regarding the content of the inclusions. If you have the option of the advanced one, then based on the results from here, you can start to calculate the concentration of certain inclusion types, which evaluated from here. Okay, and for the same set of predefined inclusion types, you have this calculation for the size distribution. Now we have quantitative. If you remember before, for this one, we have the size, but it's qualitative, small, medium, large, according to the intensity level. Now we have the quantitative size separation from the scale of macron. So for the different inclusion types, with different some groups of the macrons, you are able to see this table. And of course, the number is also normalized to cubic millimeter. The groups can be defined by user if as you want. You can even put it higher, or you can make it, for example, 1 to 3, 3 to 5, something like that. Well, that's not fixed. Well, if you don't like to have the table, then you have this plot. It's possible to plot all the 11 inclusion types that here in this report, I just made some example. So you will see this size distribution plot. And you can see, in order to show some nice plot, actually the groups of the size discrimination, I have the different setup from here. So that's something, as you can see, it's flexible. Then afterwards, you have the possibility to have ternary diagram. That is when you have additional option of the report. That's called the TD option for the report. So if you have that one, then you are able to make this ternary diagram phase, which I'm sure is quite familiar for the metallurgist. They normally use this for the melt process control. So for example, here we also only put 3 types of the inclusion system to check. This aluminum, calcium, magnesium, or aluminum, calcium, titan. So in case there, clearly this sample, they don't have quite titan treatment. And here you have also another type is aluminum calcium oxide with manganese sulfide. So that's just an example. Inside this ternary diagram, we will have the size this separation based on the color on the dot. And at the bottom, you have the table because it's difficult to count inside the plot. Okay, and afterwards, of course, it's the most important feature of the GD is the relative composition between the three components. So here we have the average concentration of the three components calculated here. That's this part. Then the last part, the field, it's one additional information to you, to customers. It's for the inclusion volume fraction, and that you already saw it from the PowerPoint of Ramak. So here, normally we will prefer to have the same groups as the size distribution table. Well, still, it depends on you. And the values here is actually already multiplied with 10 to power of 10 because it's really too small. But still, it gives you the information. In case you would like to compare the fraction, this volume fraction, to the area fraction, normally you could obtain with the microscope. Okay, so you will say that's the report, what we can get when we have the results. Another thing, when we finish the results, actually it's already sent to SPC. Because in my method here, I have the option of the SPC, and I made this automatic process. So here you see the results. Besides the concentration results, you see also the results of inclusion analysis sent to SPC. Okay. When you have here, you have the control limit which I set before. So with this one, it's easily for you to monitor the trend of your sample to see if they are within the limit or not. If you don't have that sent by default, you can still do like manually send. And when you do that, you will also see something like when it's out of limit. So that's what we see here. See, calcium aluminum ratio is too low, lower than the specified limit. So that's something which is useful when you have option of SPC directly connected with our OXAS software. The concentration normally for people who already have this statistic data control center, then normally no problem, you already know. But for this, it's quite new. You will see this. So here, you see the difference. Here, I set already the control limit. And here, as example, we don't set anything. But no problem, as long you send it to SPC, software start to generate the wrong chart, and you will see the trend of the samples. Okay, so that is SPC, what you can do. And after the two sample analysis, of course, you can, as I did before, export all the two samples to Excel to make your own comparison or study. Otherwise, if you don't do that, what you can do, if you remember, we have another software. I open here. As we said, Spark Explorer, for the people who would like to make some offline investigation. what you can do from here. You have all the channels listed here. So you can have the plot, of course. And you can decide to use the run chart or use the histogram in order to study it. The most important, you have some statistical calculations here in this software. And you can decide which number or which data set you would like to use in order to do the statistical calculation. That's here. And then you have the normal statistical calculation as average, as standard deviation, or minimal or median, something like that. But here is not the way we calculate as we applied in OXAS for inclusion analysis, because the average or standard deviation here, including all the, you see, the peak, the baseline intensity. So it's including everything. That's not what we want. We want is a normalized average intensity average and normalized standard deviation. So you see the value here. It's quite different. So here is 75 around. Here is 600 around. So it's totally different. But here is the I need to move it. Here is the way we use for calculation. And then you have the possibility to calculate the number of the peaks according to the defined threshold here. And calculate the insoluble ratio calculated for this element. So for different element, you will see all this calculation is the same calculation as we did for inclusion analysis. Okay. So that's one way we can use the Spark Explorer. There will be another way you can do it. It's you remember we made the two samples. So okay, now I want to compare the two samples. I select the results. I select some interested channels, and I want to make some run chart to compare. Okay, it's not so. Now it's easier to show. You have all the interested channels plotted. For the second sample in the second line, and for the first sample in the first line, for the all 4 elements. Now, just by look at here, it's already quite easier to distinguish. For the sample 2, actually, I really have much more peaks for magnesium. That's some quick evaluation you could have already based on this grid view. We call it grid view because it's several grids like that. And now if we would like to make additional comparison, what we can do, we can select and compare select charts. So by this way, you can see for each chart, you have same as before calculated normal distributed intensity average and standard deviation. It's already calculated. And for each chart, we have also the possibility to calculate the number of the peaks according to this defined threshold. It is here. It can be moved like that, or it can be defined here. But the most important, you see the red color. Maybe that is not so easy, but this one, you see the red color changes according to the threshold we define. So to make it simple. By this way, we can see clearly what would be the difference between the two samples. And if now we don't want to compare two samples, we can compare just one sample, different channels. Now we have all the channels listed here. And same, we can activate for the peak count or showing for all the samples, for all the channels. And then we are able to like that to investigate what would be the coincidence. And now for adjust some parameters, people can play with the threshold now to see by which way we can get more coincidence. Oh, it's supposed to have more coincidence or not. So that's the way we can play with this offline investigation tool.